You know, what really separates good code from truly great code? Well, a lot of the time, it's not about some fancy, complicated trick. It's about knowing you have the right tool for the job and when to use it. So today, we're going to open up the programmer's ultimate toolkit, data structures. I mean, think about it. How does your phone just know how to find that one contact in a sea of thousands, like instantly? Or how does a search engine sift through billions of web pages in less time than it takes to blink? It's not magic, right? It's logic. And it all comes down to how that data is organized. That's exactly what we're going to break down. So here's our game plan. We're going to start with the basics, the absolute foundation. What's the difference between data and information? Then we'll get into the blueprint, what data structures actually are. And after that, we'll get our hands dirty with the two main types, the linear ones and the nonlinear ones. Okay, first things first. You can't build a house without understanding what your bricks are made of. So before we start building anything, we have to get clear on the crucial difference between data and information. So, data. Data is just the raw stuff, random, unorganized facts, like the number 85 or the name Sharmila. On their own, they don't really mean much of anything. Is 85 a temperature, a test score, maybe an age? We have no idea. It's just a fact floating in space. But information? Information is where it gets interesting. That's what happens when we give that raw data some context. Suddenly, we know Sharmila's score is 85. See? Now it's processed, it's organized, it's meaningful. And we can actually use it for something, like figuring out the class average. And this breakdown shows it perfectly. Over on the left, you've got that raw data. Just a jumble of scores, 50, 60, 70. It's not organized and it's not super helpful. But once we process it, we get information. The average score is 60. Now that is organized, meaningful, and you can do something with it. So, at the end of the day, it all boils down to this simple but powerful little equation. You take a chaotic mess of data, you apply a structured process to it, and that's where our data structures come in, and boom, you get organized, valuable information on the other side. And that brings us right to the main event. If processing is the key that turns data into information, then data structures are the blueprints we use to do that processing in a smart, efficient way. Now, this is the classic definition, and it's a good one. The key words here are efficiently. It's not just about storing data, it's about storing it in a smart way, a way that's perfectly set up for the specific things your program needs to do and do fast. And why does this matter so much? Well, because the ops we use every single day are dealing with absolutely enormous amounts of data. Choosing the right data structure is what makes an application feel snappy and responsive instead of slow and clunky. It's the secret to writing software that can actually scale up. Okay, so let's crack open this programmer's toolkit. When you get down to it, all these different data structures can be sorted into two main families. This right here, this is our map for the whole toolkit. At the very top, everything splits into two big camps, primitive and non-primitive. We're going to touch on primitive real quick, but our main focus is going to be on the non-primitive branch, which itself splits again into linear and nonlinear. So let's just get the primitives out of the way. Think of these as the absolute basic building blocks, the Lego bricks that the programming language gives you right out of the box. Things like a whole number, a single letter, or a simple true or false value. All right, now let's get into our first major group of tools, the linear structures. And just like the name says, these are all about organizing data items one after the other, in a straight line. So think of these structures as just getting your data to form a nice, orderly line. And the most fundamental, most common tool for that job, the one you'll find in pretty much every programming language out there, is the array. An array is basically just a row of numbered boxes, all sitting right next to each other in memory. The two big rules are, every box has to hold the same type of data, and you can instantly jump to any box you want just by using its number, its index. Oh, and a crucial little detail for all you programmers out there, that numbering almost always starts from 0. Okay, next up are two structures that are all about the rules for getting in and out of line. On one side, we have a stack. It works on a last in, first out principle. Just think of a stack of plates. The last plate you put on top is the first one you take off. Then you've got a queue, which is the exact opposite. First in, first out. This is just like a line of people waiting for tickets. First come, first served. And we can see exactly how they work here. With a stack, you push a new item onto the top and you pop an item off the top. But with a queue, you enqueue an item at the very back and you dequeue an item from the very front. They might seem similar, but they enforce two totally different rules about order.
Now let's grab our other set of tools. So far, everything has been in a nice, neat line. But what happens when your data's messier, when it's all interconnected? For that, we need nonlinear structures.
And this really says it all, doesn't it? Linear data is sequential, like a single file line. But nonlinear data is hierarchical. It's a network with multiple layers and all sorts of complex connections. There's no simple next item here. Instead, you've got parents, children, and interconnected neighbors. The classic example of this is a tree. It's a structure built specifically for hierarchical data. You start with one root node at the top, and that branches out into child nodes below it. A perfect real-world example is the file system on your computer, or even an org chart at a company. It's the perfect tool for any kind of parent-child relationship. And last but not least, we have graphs. Now, if a tree is a strict hierarchy, a graph is basically a free-for-all network. It's just a bunch of nodes, we call them vertices, and the connections between them, which we call edges. Think about a social network. People are the nodes and friendships are the edges. Or a map of cities connected by roads, that's a graph. Okay, wow. So we've seen arrays, stacks, queues, trees, and graphs. A whole toolkit full of different options for organizing data. Which, of course, begs the question, out of all of them, what's the single best data structure to use? And the answer is, there isn't one. There is no single best data structure, just like there's no single best tool in a toolbox. You wouldn't use a hammer to saw a piece of wood, right? The real skill of a great programmer isn't just knowing how to write code, it's looking at a problem and knowing exactly which tool to pull out of the toolkit. And making that choice, that's the real secret to building amazing, efficient, and powerful software.